Hello students, welcome to lecture 32 of this course. In the last lecture I discussed about principles of NMR. I started with the 1D NMR and I introduced how to represent signal and what are the factors on which signal depends. In this lecture I will discuss how to get a structure information from NMR. So, we will start with the structure determination of organic compounds. 4 different features of proton NMR spectrum provide information about a compound structure, and the 4 different features are number of signals, position of signals, intensity of signals, and the splitting of signal. Splitting of signal is for features gives important information through which we can derive the structure of organic compounds. I will go one by one to each of the features and discuss the importance of those 4 features. First feature is number of signals. So, the number of NMR signals equal the number of different types of proton in a compound. So, if there are 4 different kinds of protons in a compound, you should expect 4 different signals. Protons in different environments are called non-equivalent protons and they give different NMR signal, whereas protons in same environment are called equivalent protons and they will give same NMR signal. So, proton in same environment gives same signal, whereas proton in different environment gives different NMR signal. For example, if you take this case, this is your dimethyl ether, all 6 protons, 3 protons attached to this carbon, 3 protons attached to this carbon has same environment. So, any one of the proton is attached with one carbon and that carbon is attached to one oxygen and again that oxygen is attached to one carbon. So, environment of any of the proton which you take in dimethyl ether is same. What does that mean is that proton has only one kind of environment and so you will get one NMR signal. Now, take this case 1 chloroethane or ethyl chloride. These 3 proton has same environment, whereas these 2 proton has same environment, but different than these 3 protons. So, 1 chloroethane has 2 different kind of protons and so you will get 2 NMR signals. If we take methyl ethyl ether, there are 3 different kind of proton. For example, if you see these 3 protons are in same environment, whereas these 2 protons are in different environment than these 3 protons, whereas these 3 protons again is in different environment than these 2. And so, you have 3 different kind of protons and so you expect 3 NMR signals. So, number of signals gives you an idea about how many different kinds of protons are present in a molecule. Now, take this case 1 chloro, 2 chloroethane. In that case, all protons have similar environment and so they will give one NMR signal. In this compound, whereas this is 1 chloro and 3 bromo, 1 chloro and 3 bromo propane, there are 3 different kind of protons, and so there will be 3 NMR signal. So, you see this carbon, these protons, these 2 protons, they are attached to the carbon, which is attached to a Cl group and a C group, whereas these 2 protons is attached to carbon, which is attached to 2 different carbons, whereas these 2 protons are attached to a carbon, which is attached to a bromo group and 1 carbon group. So, these 2 protons, these 2 protons and these 2 protons are in different environment, and so you should expect 3 NMR signals. In this compound, we have 2 different kind of protons, and so there will be 2 NMR signals, whereas in this compound there are 3 different kind of protons. These 3 hydrogens has different environment in comparison to these 2 hydrogens and this hydrogen. All the 3 types of protons have different environment, but these 3 protons, they have similar environment, they have same environment. So, these 3 protons do not differ in their environment, and so they are known as one kind of protons, whereas these 2 protons also have same environment, and so they are called of same type, of the same type. But in between these 2 groups, their environment are different, and that is why they are assigned to different groups. In comparing 2 hydrogen atoms on a ring or a double bond, 2 protons are equivalent only if they are cis or trans to the same group, cis or trans to the same group. For example, if I take this proton, this is cis to this chloro group, whereas this proton is also cis to chloro group, and hence these 2 protons are same, and so we expect only one signal. But if you take in this compound, this proton is cis to chloro group, whereas this proton is cis to bromo group, and hence these 2 protons do not have same environment, and so we get 2 NMR signals. In this compound, you see this H B basically is cis to this chloro group, whereas SC is cis to HA group. So, these 2 protons are different, these 2 protons are different, and this is different since this H is attached to carbon, which is attached to this chloro group, whereas these 2 protons are attached to carbon, which is not attached to chloro group. So, all 3 protons are in different environment, and so we should expect 3 NMR signals, and that is what we get. Now, the second feature of the NMR spectrum is position of the signal, which is basically chemical shift of the proton. So, chemical shift of proton also gives an idea about the functional group, The most important part about the chemical shift is that the less shielded the nucleus becomes, the more of the applied magnetic field it fills, and this I have already discussed about the chemical shift in the last lecture. Why in certain case chemical shift is high, why in the certain cases chemical shift is at small delta value. the main factor is shielding of nucleus. The de-shielded nucleus experience a higher magnetic field strength and it needs a higher frequency to achieve resonance. Higher frequency is to the left in the NMR spectrum and towards higher chemical shifts. So, de-shielding shifts and absorption downfield. Protons near electronegative atoms are de-shielded. So, they absorb downfield and again absorb downfield means higher chemical shift. So, these are the things which I have already discussed in last class. So, please look at the content of the last class. So, if you take a proton and if an electron says this proton, then your peak shifts upfield. That is what it is written, that electron says the nucleus and proton in presence of electron around the nucleus basically shifts the absorption upfield. If somehow we decrease the electron density near a nucleus, we are basically de-shielding it. And in that case absorption shifts downfield, and again downfield means higher chemical shift, whereas upfield means lower chemical shift. In last class I started discussing about factors influencing chemical shift. Again I will start with electronegativity. The surrounding electron density of proton says the nucleus from external magnetic field. So, if I have electron withdrawing substituent attached to a nucleus, they can be attached to the same or adjacent nucleus. It basically de-shielded proton and resonance occurs at lower field or higher chemical shift. So, if electronegative atom is attached to the carbon to which these 3 protons are attached, they will take away electrons from the carbon and proton, and that is how they de-shield this proton. And resonance of these protons happens at lower field, and that means they have higher chemical shift. As you go down, electronegativity decreases when you go down from fluorine to chlorine to bromine to iodine, and so less electron will be shifted from the proton, and so de-shielding will be small, and hence resonance will occur at higher field or lower chemical shift. And so you can see that as you go down, the chemical shift value decreases. In alkane, the carbon is attached to R group, which is electron donating group, and that is why you expect a small chemical shift. The second effect which we started discussing in the last lecture, which affect chemical shift, is Mesomeric effect. Again, Mesomeric effect can withdraw electron from the proton, or it can enhance the electron. Electron surroundings of a proton. If it removes the electron, then we expect chemical shift to be higher. If it donates electron, then we expect chemical shift to be smaller, and that is what we see here. If we go from simple alkene to an alkene substituted with COCH3 group. The CO group is in conjugation with this double bond, and so there will be mesomeric shift, and shift will be in this direction. And so, what you are doing is you are removing electron from this proton, and so this proton will be in resonance at higher chemical shift. In this case, when double bond is attached to a lone pair, plus M effect will operate, and proton is going to have more electron. This proton is going to have more electron, and so this proton will resonate at frequency which is lower. So, chemical shift will be lower, 3.74. And similarly, we can discuss about monosubstituted rings. Here, if the ring has NS2 group, its lone pair is in conjugation with the double bond, and the lone pair is will be, if you take this lone pair here, then this will go at this position and this will go to this position. And so, you can see that this is going to be of higher chemical shift, and these two are going to be of lower chemical shift, since here electron is reaching. This proton is more electron rich, this proton is more electron rich. So, NS2 has plus M effect, and so the protons at ortho and para position are going to be more rich in electron, and hence they will have lower chemical shift. Again, OMe has plus M effect, and so proton at ortho and para position are going to have lower chemical shift comparison to a proton at meta position. CH3 is electron donating group, and this has plus I effect, and so this proton will be more electron rich compared to a proton at your meta position, and hence this will have lower chemical shift in comparison to a proton at para position. NO2 is electron withdrawing group, so it has minus M effect, and so proton will be less rich at ortho and para position, and so they are going to have higher chemical shift. So, the electron around a nucleus will affect its chemical shift value. If there is more electron near a proton, then it is going to have a smaller chemical shift. Now, here you see the effect of mesomeric effect, and at this position comes the benzene ring. If I put NS2, then it will go to lower chemical shift. I put OMe, it will go to lower chemical shift, whereas if I put NO2 on the benzene ring, it will go to higher chemical shift. So, this is line for benzene ring. NO2 is withdrawing electron away from the ring. So, all proton either in ortho position, para position or meta position is going to be electron deficient in comparison to benzene ring, and so your chemical shift will be high. Whereas these three groups, NS2, O, CH3 and CH3 group, they are donating electron, and so they are going to be at higher chemical shift than benzene. They are going to have higher chemical shift than benzene. The electron donating plus M effect will be more predominant in ortho and para position, and so ortho followed by para position is going to be of a smaller chemical shift. Meta position will be of highest chemical shift. Meta will be of highest chemical shift. Proton at meta position is going to be of highest chemical shift among all these three protons. Same is the case with OCH3 group, and you can see ortho, para, and then meta. So this is the effect of the substituent on a benzene ring. Now, third effect which I am going to discuss is hybridization effect. Hybridization of carbon will also affect the chemical shift value. Order of electronegativity, as we know that a nucleus with hybridization sp is going to be more electronegative than a nucleus which is sp2 hybridized, and similarly a nucleus which is sp2 hybridized is more electronegative than a nucleus which is sp3 hybridized, and that is because of S character. So, if S character increases, electronegativity is more. So, if protons attach is with sp3 carbon, then the proton chemical shift is going to be in 0 to 2 ppm range, and some value is given here. This is for proton attached to tertiary carbon, and since proton attached to tertiary carbon, here proton is attached to secondary carbon, and among these three you just apply the concept of electronegativity, and you will understand why this one has higher chemical shift and this one has lower chemical shift. sp2 carbon, if we compare between sp2 carbon and sp3 carbon, we know that sp2 carbon is more electronegative than sp3 carbon, and hence if proton is attached to sp2 carbon, then electron is withdrawn from that proton more strongly in comparison to a proton attached to sp3 carbon. So, we discussed about the substitution effect on proton chemical shift of benzene ring, but the very high chemical shift value cannot be explained just only based on electronegativity. Value of chemical shift can only be explained on the basis of anisotropy. The circulation of electrons around benzene ring produces a ring current in the presence of an external magnetic field. So, there is a circulation of electron in the plane of benzene ring, and that produces a ring current in the presence of external magnetic field, and this causes the protons in molecular plane to be deshielded, and protons above or below the plane to be shielded, and so benzylic protons, aromatic protons has very high chemical shift. It is 6 to 8.5 because they are deshielded, whereas protons in above protons above or below the planes are shielded, and that is why they have low chemical shift value, low chemical shift value. Similar to aromatic ring, anisotropy also plays a role in double bond, in double bond. So, similar to aromatic ring, there is a de-shielding region in the plane of the double bond, and thus vinylic and allylic protons are downfield shifted. Vinylic and allylic protons are downfield shifted, and this is the value of vinylic proton. Anisotropy also affects acetylene protons. The electron circulation around the triple bond pi system takes place in such a way that protons attached to a triple bond experience a strong diamagnetic field resulting in unusual upfield shift of C triple bond C H signal, C triple bond C H signal. So, this is unusual upfield shift. Anisotropy of the carbonyl group, again protons in the plane of carbonyl group is strongly de-shielded due to anisotropy of C double bond O, and thus aldehydic protons and formyl protons of format esters are de-shielded and appear at higher delta value. So, if it is de-shielded, then higher delta value. If it is shielded, then it is going to have lower delta value, lower delta value. So, please keep that thing in mind. Chemical shifts are also affected by hydrogen bonding. So, there is a downfield shift of OH, NH and SH proton if they are hydrogen bonded. So, they will come at your high chemical shift value. Carboxylic amide and sulfonamide NH protons are downfield shifted in comparison to their related amines due to their acidic nature, and that is why these NH protons will come at higher chemical shift value. Acidic protons have higher tendency to form hydrogen bonding. Similarly, OH group of phenol and carboxylic acids are downfield shifted in comparison to aliphatic alcohols. Aliphatic alcohols, and this is your a typical chemical shift value of some of the groups. So, RCO2H has highest chemical shift, whereas you can see that these values, these amine values CHRNR2, these are going to have lowest chemical shift value. Saturated alkanes has lowest chemical shift value. If you look at R2C double bond CH2, it is having higher chemical shift value in comparison to your this triple bond RC triple bond CH, and this is because of anisotropy. This is because of anisotropy. This is because of anisotropy. And then you can see here that alcohol, and compare between this alcohol and RCO2H group. So, this acidic protons is more downfield shifted or higher chemical shift compared to an alcohol proton. It is because of they are very acidic. They are very acidic. So, this proton of your aldehyde is going to have higher chemical shift value, because of anisotropy. So, these are the sum of the values of chemical shift, and depending on the value of chemical shift also you can guess, depending on chemical shift of the proton which you obtain through NMR, you can tell that which kind of functional group may be present in that compound. The third important factor is intensity of the signal, and the area under an NMR signal is proportional to the number of absorbing protons, and this can also be used to obtain structural features from a NMR spectrum. Modern NMR spectrometer automatically calculates and plot the value of each integral in arbitrary unit. The ratio of integral to one another gives the ratio of absorbing protons in a spectrum, and that is very important. Note that this gives a ratio and not the absolute number of the absorbing protons. So, please keep this thing in mind, but it is important that if I get the ratio of integral, I know what will be the ratio of absorbing protons in a spectrum. So, now see in this case, this is your CH3O C CH3 thrice. Now, if you notice, they have two different kind of protons. So, you get two signals, and now just based on their intensity, you can tell that which proton gives which signal. So, now here you see there are only 3 protons and there is 9 protons here, and so what you expect that if we normalize intensity, this should be in the ratio 1:3. And now you see if you look at the intensity, this is 20 unit. If this is 20 unit, this is your 60 unit. This is your intensity of the signal. And so, now you know that ratio of protons having this signal is 1/3 of protons having this signal. So, it is quite easy to assign. This is CH3 thrice C and this will be CH3O. This has 3 protons, this has 9 protons. So, it is quite obvious that the signal of this peak will be thrice that of signal of this peak. So, just based on intensity, we are able to assign the spectrum in this case. Now, let us think about this molecule. So, this is NS2, CH2 and CH3 twice. So, this is CH3 and this is CH3. Okay, so, 3, 3, 6 and there is 2 proton attached to this carbon, 2 proton attached to this carbon and 2 proton attached to this nitrogen. So, you have 4 different kind of protons, So, you expect 4 different signal and these 4 signals are here. And if you look at this intensity ratio, here is the ratio given and this is 1:1:3:1. So, this is the ratio which we obtained from the spectrum, NMR spectrum, which you obtained through the NMR experiment. And the intensity what you got is in the ratio of 1:1:3:1, 1:1:3:1. Now, look at the total number of protons here 2, 2, 4, 2, 6 and 6, 12. So, total number of proton is 12 and the sum of this is 2 plus 3 plus 1. So, 5 plus 1 6 and if I divide 12 divided by 6, this will give you 2 and so just you multiply this number by 2. So, equivalent hydrogens will be your 2. So, one equivalent hydrogen group will have 2 protons, the second group will have 2 protons, and third group is going to have 6 proton, and fourth group is going to have 2 electrons. So, there are 6 plus 6 12 protons, 2 plus 2 plus 6 plus 2 is 12 protons, and if you see the third one, it has a 6 protons. So, certainly you will be able to assign this peak to these 6 protons, because this is almost thrice of other peaks, and the others can be assigned based on the chemical shift, This B is going to be most upfilled, since this proton is attached to an electronegative atom N. So, B will be this, C will be this one, and since this the proton attached to this carbon, and carbon is attached to NCH3 twice group, which is less electronegative than NH2 group, because this N is attached to electron donating group, and so the NCH3 twice is less electronegative than NH2, and hence the second will come at this position. Third we have already assigned, and fourth, since this is attached to, and it is attached to N group directly, and so it will come at this position. So, just based on what we expect of chemical shift value, we can assign your this spectrum. There are another characteristic, which is the splitting of signal. I will discuss that also. That basically ensures that the spectrum is correctly assigned. So, the fourth feature, another important feature of the NMR signal, is they split in presence of each other protons, and that is explained by scalar J coupling or J coupling. So, if there are two spin, adjacent to each other, they will split the signal. To explain this, let us assume that this spin is given by I and this spin is given by S. This spin is given by S, and if spin is in this direction, then I give this alpha sign. If the spin is in this direction, then I give it beta sign. So, the two spins can arrange in 4 different ways. First, when both are up. In the second one is up, another is down. The third one is up, another is down, and the fourth one, both are down. So, in this, the spin of both I and S is up. In this, spin of I is up, spin of S is down, and so spin of I is given by alpha, spin of S is given by beta. In this, spin of I is down and spin of S is up, and so beta alpha. So, these are the 4 different states, and if the transition happens from alpha to alpha beta, it means the S is changing sign. So, S is going from alpha to beta, whereas for I the sign is same, alpha, and that is why this is called S1 transition. This one is known as S1 transition, and similarly if you look at this beta alpha to beta alpha to beta, the change in sign is happening for the spin S, and that is why this is known as S2 transition. Whereas, if you see this transition alpha alpha to beta alpha, the spin of I is changing direction, it is going from alpha to beta, whereas in this also spin of I is changing direction, and that is why these are known as I 1 and I 2 transition, I 1 and I 2 transition. So, now you can see that we have two S transition and two I transition, and that is what we say that in presence of S, the I transition is split into two parts, whereas in presence of I, S transition is splits into two, and that is what is shown here, and this is for I. So, this is your chemical shift of I, suppose, and then in presence of your S, it is splits into two. One is I 1, I 2, and the splitting between these two signals is known as J value or scalar coupling. Here you see the S also splits into two because of presence of I, and this is your chemical shift of S, and split is in the other two direction, and this gap between these two value is known as J, is your J value or coupling constant value. So, the presence of nearby proton split the signal of protons. So, let us talk about some molecule and see how many splitting is possible. So, take the case of ethyl iodide, and this carbon has 2 proton, this carbon has 3 proton, and if I look at the splitting of this HA, due to this HB. Now, think of how many levels it will split. So, this is for HA, and now you see all HB can be up direction, 1 is down, 2 is up, and there are 3 different possibilities possible for 1 down, 2 up. For 1 up and 2 down, these 3 are possible, and for 3 down, this 1 combination is possible. So, splitting will happen, the signal of HA will split into 4 with this intensity ratio 1:3:3:1. This ratio because there is only one combination for all 3 spin up. There are 3 different combinations for 2 up, 1 down, 3 different combinations for 1 up, 2 down, and 1 combination for all 3 down. And so, the relative intensity of quartet will be 1:3:3:1. So, the signal of HA splits into 4 because of presence of 3 HB protons, and that can be converted into rule that if there is a n protons nearby, then there will be the splitting of nearby proton will be in n plus 1 peaks. So, 3 protons are present. So, signal of HA will split into 4, and since 2 protons are present near to these HB protons. So, the signal of HB will split into 3, 2 plus 1 3, and that you can see here that if we go for Hb, then what happens that possible spins are combination of both up is 1, the combination of your 1 up and 1 down is 2, and combination of both down is 1, and so split will be in the 3 peaks in ratio 1:2:1, 1:2:1, 1:2:1. So, from this example comes what is known as n plus 1 rule. A hydrogen nucleus with n adjacent hydrogen nuclei will split into n plus 1 peaks. Nuclei will split into n plus 1 peak. And what does that mean is coupling is with 0 protons, there is no nearby protons, then you will get only 1 peak. So, 0 plus 1, 1 peak. If coupling is with 1 proton, you will get 2 peak, 1 plus 1, 2 peak in the ratio 1:1. If the coupling will be with the 2 protons, the peak will split into the proton peak will be split into 3 different peaks with the ratio 1:2:1. When coupling is with 3 protons, 4 peak will result with the intensity 1:3:3:1. Coupling with 4 protons will result into your 5 different peak with the intensity 1:4:6:4:1, 1:4:6:4:1. When a proton is surrounded by more than one type of protons in its adjacent carbon, then a conjugate splitting pattern will be observed. A conjugate splitting pattern will be observed. For example, here if you see Ha, Hb, Hc, they are all different types of protons, all different type of protons if the substituents are x, x and y at this position. Ha and Hc, Ha and Hc are expected to couple with Hb, only, and so since there is coupling of Ha with Hb, and so this will split into 2 peaks. Sc will also be split into 2 peaks, but interesting is your splitting of Hb, since it will be split both by Ha and Hc, and the splitting will like be this. So, Hb this is splitting because of its coupling with A, and this is the splitting, and now since B is also coupled with C, and so these 2 peak again will split, and this is your coupling constant between A and B, and this will be the coupling constant between B and C. So, there will be 4 peaks, but this is called 2 doublets or doublet of doublet, DD, doublet of doublet. Which splitting is larger depends entirely on the chemical nature of other surrounding group. So, ZAB is higher or ZBC is higher, it will depend on chemical nature of other surrounding group. If the coupling constant of the different splitting levels are equal, DD will appear as a simple n plus 1 triplet, So, look at here, this the second one, the J12 is equal to J23 if you take this molecule. This proton is being split by this proton and this proton, but the coupling constant is between 1 and 2 and 2 and 3 is equal, coupling constants between these 2 and these 2 are equal, and that are equal to 8 Hertz. In that case, we will get a triplet. In that case, we will get a triplet. So, appearance of DD depends on the relative J value, and if J1 is equal to J2, we looked at this triplet we will get. If J1 is equal to 0.5 J2, then you will get like this. Then depending on the different values, you will get different kind of DD signal. Now, there is doublet of doublet of doublet DD signal also present. In cases where this happens when one proton Hb is split by 3 other protons, Ha, Sc and Sd, each chemically different from itself, a doublet of doublet of doublet pattern is formed. Each line in final DDD pattern would have same intensity, since each doublet itself has 1:1 intensity while splitting. So, let us look here. This is the first splitting, and then this gets splitted. This is the second splitting, and this is your third splitting. This is your third splitting. So, this is because of coupling between A and B, this is because of coupling between B and C, and this is because of coupling between B and D, and so doublet of doublet signal will be seen. Then there is a 2 bond 2J coupling, commonly known as geminal coupling. They are usually smaller in magnitude than 1 bond coupling. So, this is your geminal coupling, and you can see that C is attached to this H, and this is known as 2 bond 2J coupling, 2 bond 2J coupling, and some 2 bond coupling constant are given here. So, between proton and proton you will get this 9 to 15 hertz, and these are between proton and D, this is between proton and fluorine, this is between proton and carbon, this is between proton and proton attached to sp2 carbon, this is between 19F and 19F, and this is between proton and 31 phosphorus. Geminal coupling increases in magnitude as the bond angle alpha decreases. So, this alpha value affects the coupling constant value. Geminal coupling increases in magnitude as the bond angle alpha decreases, and due to high electron spin correlation. So, if this is 120 degree, alpha is 120 degree, then it is 0 to 2 hertz. If it is 118 degree, then coupling increases to 5 hertz. If it is 109 degree, then coupling is 12 to 18 hertz. Angle is 107 degree, the coupling is 17.5 hertz, 17.5 hertz. Similarly, there is also coupling between 3 bond, and that is very important if you want to get dihedral angle. So, there is a relation between coupling which is for 3 bond edge coupling, for example, this proton, 1 bond, 2 bond and 3 bond, this proton and this proton. If we can get coupling constant, they can give you the dihedral angle between these 2 proton. So, Martin Karplus showed that J from vicinal coupled proton atoms depends on dihedral angle between the protons, and this relationship can be approximated by the famous Karplus equation, and J value is given by A cos square theta plus B cos theta plus C, where A, B, C are empirically derived parameters, and this is very important if you want to estimate the molecular conformation. Today I will stop here because time is over, and in the next lecture I will discuss about how to get the structural information using 3 different kind of information. basically 4 different kind of information. I have only discussed I believe 3, or I have discussed all 4. I have discussed 3. Fourth is still I am discussing. In the next lecture, I will discuss about the Koji and other 2D experiment, which are generally done to get a structure of complex molecules. Thank you very much. Bye.